Brief introduction about who I am and where I'm from, basically. So my name is Hari. I'm actually part of AI Society. So it's basically a club on campus. We focus specifically with the ML and AI stuff within the realm of computer science. We do a couple of things. We used to do like projects with industry. We did research projects, and we also do teaching as well. So today we're going to do like a workshop that's very practically oriented. So especially since you guys are here for hackathon, we'll be using TensorFlow and Keras to build 3 deep learning machine learning models for the first half. And if you guys want to continue, the second half will be basically a continuation of the machine learning in the first half. So yeah, my name is Hari, and that's the introduction. So if you guys didn't get a chance to, you guys can clone the repo. Just to reiterate, we'll be doing everything on Google Colab, which if you guys don't have experience, I'll go over with you. It's really simple, where we'll be running the code, getting the data and everything, including running our models all on the cloud. So the code is just here for you to see it, in case you want to go back and reference the code, and it'll be open source for the rest of the hackathon. And yeah, you can just use the code snippets that I give you here if you're going to be training models for your projects for the hackathon. Okay, so the stuff we're going to be implementing, we'll be implementing 4 neural networks. Does everyone here have experience or know what a neural network is? Okay, can you explain it? You said you do? Oh, you did? Okay. Okay, go ahead.
So it's basically you have input nodes and you have output nodes too, and a bunch of hidden layers. Basically what that does is that it has a different function in it, and it's going to manipulate the input and then different outputs.
Yeah, that's perfect. Okay, so yeah, so you can see on the diagram, this whole workshop, we're going to just be building neural networks for different tasks. So we're going to be doing 3 exercises in this part. One is MNIST classification. The other would be Cypher10 classification. These are image data sets, we're going to classify them, and then finally autoencode. But basically what neural networks are very simply universal function approximators. What that means is they take a very complex input, perhaps an image, and then they output something. So they ingest an input and they output something, just like a function. But unlike a standard linear function, they have very many layers, like he just said. They might have a lot of hidden layers, and they have a lot of nonlinear mappings that make it so that they can go from really complex input to really complex output. So essentially, they're just function approximators. So what we're going to do focus on for this workshop is Keras. I think a lot of you probably have heard of TensorFlow and Keras. Can I get a show of hands of who's heard of TensorFlow? Okay, so TensorFlow is basically, TensorFlow and Keras are both deep learning libraries. What that means is they provide a lot of the functionality for you to code your machine learning models. Essentially, they give you a lot of prepackaged functions like optimizers or model building that allows you to easily build models without having to write everything from scratch. That's what they do. And Keras, since TensorFlow got updated to 2.0 earlier last year, Keras is basically a high-level wrapper on top of TensorFlow that makes it extra easy to build networks. So what we're going to focus on this workshop is Keras, which is really the easiest way to build networks out there. And in particular, we're going to do 3 models. I'll go more in detail with all of these things in the next few slides. The first is sequential. So this is a really fast and easy way to get your models running or to get it up in training, but it's not very flexible. I'll go more into detail why it's not flexible. And then functional API, that's the second thing we're going to do. We're going to classify basically images of 10 different things. So the classes will be like ship, dog, cat, animal, and we're going to train a model to classify the images into 1 of 10 categories. That will do with the functional API. This one is pretty flexible and also pretty easy to implement. So if you guys are going to be using neural networks for this hackathon, you can probably use the functional API. It's pretty fast and pretty flexible. And the last is Keras subclassing. So this is the most flexibility. You can do the most stuff with this, but it's also the hardest to implement. So the last exercise we're going to do is with model subclassing. We're basically going to create an autoencoder. It's a model that allows you to compress data. So we're going to take in images, compress them, and then view their uncompressed version. And we're going to do that with subclassing. It gives us a lot of flexibility, but it's hard to implement. So unless you have something really complex you're going to do in this hackathon, or like something you can't find, you just cannot do with functional API, I would stay away from it. But I'm going to show it to you because it allows you the most flexibility. And if you want to continue projects beyond this hackathon or do research or something like that, subclassing is probably a good way to do it. Okay, so sequential models. Basically, I'll just get into the workshop. So what everyone can do is, if you have a computer, you can go on to colab.research.google.com. So it pulls up a page like this. And what you want to do is you want to click New Python 3 Notebook at the very bottom. So we'll just get everyone on there. So colab.research.google.com, it's associated with your Gmail account, Google account. So it should be pretty easy to use. Okay, so I already have one open, so I'm just going to pull up my existing notebook. So what Google Colab is have any of you guys used Jupyter Notebooks? Can I get a show of hands who's used Jupyter Notebooks? Okay, so it's exactly what Jupyter Notebooks is, but it's on the cloud, and you also get GPUs and TPUs for free, so hardware accelerators for free. So if you don't have access to an NVIDIA GPU on your machine and you want to train big models that just take forever on your laptop, you can just do it on the cloud for free with Google Colab. The second part about this is it's Jupyter Notebook style, so you write code into the editor, and then you basically click blocks. You just run blocks at a time. So it's easier to debug. So we'll just get right into the code. So the first thing we're going to do is we're going to import TensorFlow 2. So what we do is we do a try-catch block, and then this is probably easier. Okay, and then the percentage sign says that we're going to run a command. So it's a particular type of command. We're going to do a TensorFlow version, and we're going to do 2.x. So what this says is we're going to use TensorFlow 2.0. It's the latest version of TensorFlow. It got released earlier last year, so it cleans a lot of the API and makes it pretty easy to do. And then we'll just do an exception, and we'll do pass, and then just run the code block here. So what it should do is it will run, it takes a little bit of time because you're changing the runtime, you're changing the default installation of TensorFlow, but now you have TensorFlow 2 on your Colab machine. So I think this stuff is pretty easy, so now you can easily just have TensorFlow 2 on here. Is it okay to see? I think the color is off, but if you're having difficulty seeing, you can always go back to the code that you just cloned, and it's all there. So don't need to worry too much. Okay, so next step we're going to do is we're going to import everything. So I guess let me just do one thing, so I'll just make it clear. So the task we're trying to solve right now is this task. So have you guys heard of MNIST? It's a very famous, MNIST, okay. So it's basically the beginner's guide to machine learning. It's basically a list of 60,000 handwritten digits that we want to train a model to classify. Each of these digits that are displayed there, they're from 0 to 9, so it's 10 digits, 10 classes of things that we need to classify. And there are 28 by 28 grayscale images. So each of the images is encoded as a 28 by 28 array, and the values of them is just grayscale, so from 0 to 255. So we want to take this input and then produce an output. So that's our problem, just to make it extra easy. Okay, so next thing we're going to do, we're going to import everything that we need. So TensorFlow as TF, we're going to import NumPy. And finally, we're going to import, so the next one is kind of important. So what we're going to do is we're going to import Keras models. So this is like the model structure, the model class that we use to train everything else. So from Keras models, we import save model and load model. So this is going to be used a little bit later, but basically if you train a model with this method and you want to save it so that you can use it later, you want to save it on disk, you can use the save model. It will store the code into a H5 file. It's basically a big array, and then you can load that again. And then finally, we're just going to import matplotlib. So matplotlib, pyplot is PLT, then we just enter into that. Okay, so we got all the imports done. So now what we're going to do is we're going to load the data. So the data I told you earlier was this MNIST data, 28 by 28 by 1. we have 60,000 of them. So because this is a very universally acknowledged data set, it's pre-installed onto Keras. So all we have to do is mnist is equal to tf.keras.datasets, and you can see with Colab, you can just type and then it'll just pull up stuff. So mnist is popping up right there. So we can take a look. So this is our mnist data set. So what this mnist data set actually contains is a tuple of 4 things. Okay, so the first thing it contains is the X train and the Y train. This will be illustrated more when I print out these things, but basically we have 60,000 28 by 28 images, and it's separated into 2 sets, train and test. The train consists of 50,000 of these images, and the test consists of 10,000 of these images. So if you guys can't see well, just remember that the code is on GitHub, so you can access that easily. So we also remove the X test and Y test. And then one more thing we're going to do for pre-processing. I mentioned earlier that the input and the input images are grayscale images, so they're encoded as 0 to 255. Each value in the 28 by 28 pixel range is a value from 0 to 255. That's what grayscale is. So what we'll do is we'll divide that by 255 to make it easier for the model to train. This is called normalization. If you have very large values inside your network, it's going to be pretty hard for the model to learn. So we'll go ahead and run this. So what it does is it pulls the data and then automatically downloads it onto our Files tab. So it's automatically loaded and it's now on the RAM of this machine. So it's very easy to use. Later on, we'll talk about how bigger data sets that can't fit on RAM are loaded, but for now, this is how it looks. So to kind of illustrate what this is, we'll just print out xtrain.shape. So this tells you the array dimensions, and we'll also print out ytrain.shape. So this is pretty easy to see, but what it says in the top is that it's a 60,000 by 28 by 28. So what that says is there are 60,000 training images in our data set, and each of these images are encoded by 28 by 28 pixels. And then similarly, the Y train is 60,000 numbers from 0 to 9. So any questions so far? Okay. So next I'll get started on actually modeling the code. So we can also print out ytrain.shape just so you guys xtest.shape.
Could you zoom in on the text?
Oh, sorry. Like that. So yeah, just like make sure nothing's on the screen. Okay. You don't need this for now. Actually.
Can you increase the font?
Is it too small?
I can't really see it in here.
Okay. Is that better?
Yeah.
Okay. We'll have to get rid of that later, but yeah. Okay. So next what we're going to do is we're going to actually start implementing the model. So the first thing we'll need to do is we'll actually need to put our layers. So what he was saying earlier, he was talking about how the code needs to be, basically the network is an input and then a number of layers and then to an output. So the first layer that we're going to do is actually called a flattening layer. So this layer, what it does is it takes the input, which is the to 60,000 by 28 by 28, and then flattens it out to 60,000 by 784 by 784. So why it does this is, we want to compress the image that goes through the layer. If we look at it right here, basically the input to our model is going to be a 60,000, an array of 60,000 rows by 784 columns. Right now it's actually stored as 60,000 by 28 by 28. It's a 3D vector, it's like a 3D tensor. So to make it able to go through our model, we're going to actually compress it down. Okay, so the next thing we'll do is, we'll do our first, so we'll call this layer 1 maybe. Yeah. Layer 2. Let me just do one thing to make sure everything's fine. Okay, so next thing we're going to do is we're going to have our first layer that actually does stuff. So what this layer is going to be is called a dense layer. So to people who don't really have experience with machine learning, what this does is it takes the input, which is 60,000 or 50,000 by 784, and it changes the dimension size of the 784 size, basically the feature size. So right now our images, each of them are encoded by a vector of size 784. But what we want to do is we want to take that and we want to change the dimension size. We basically go through a dense layer that takes a matrix, multiplies it by what we have so far, and then produces another matrix. So what we'll do here is we'll actually change it to 100. So in this layer right here, what we're going to have is, our network is going to have an n by 784 size. So with the stuff that goes in, after this layer, after layer 1, it becomes n by 784. After this layer, it will become an n by 100. So the feature size of the image has now changed. It has gone through one transformation. So this is basically the first step. And we will have an activation. So activations, does anyone know about activation functions here or what they do in ML? Basically, they are nonlinear mappings. So we multiply one matrix by another, but what we do at the end of that multiplication is we apply basically a nonlinear function. Some of the common ones include sigmoid, but what they do is they take the output of whatever is in the output and they apply another function into it. So one of the most common ones is sigmoid. I don't really put it here, but we're not going to use sigmoid, but it looks something like this. So after taking the output of every node, we apply a sigmoid activation and you get this value. So this is the first thing that we do. So the particular thing that we're doing is called relu. This is the activation function we're going to do. So after the output of each node, we're going to apply this activation function. So we'll just call it tf.nn.relu. And then we'll call this one more time. So we'll have two layers like this. So layer 2, layer 3. And then the last layer is the logics layer. So we go through two levels of layers, and at the very end, what we need to output is we need to output a vector of size 10. The reason we do that is we are trying to predict something like the handwritten digits out of 10 classes. So from 0 to 9. So the last layer, what we do is we have a tf.keras.layers.dense, same thing. But this time we do 10 because we're trying to predict 10 different classes, right? And finally we change the activation function to something called tf.nn.softmax. So what this last layer does is it outputs a probability distribution. So after it goes through the network, we want to predict the probability that the image is in each of these 10 classes. So if the probability that it is a 0 is 95%, then the network will say that this image is a 0. If the probability that it's 9, so the ninth basically the index of this final array is 95%. That's the most probable outcome. It would pick 9. So, are there any questions about this network so far? Is everyone following me? Yeah.
Can you explain level 3 once again? How does the output work after you apply? And
Okay.
why did you stop at level 3 and didn't go 4, 5, 6?
Okay, yeah, no worries. So layer 2 and layer 3 basically goes back to an n by 100. So layer 2 and layer 3 go to n by 100. The way you can tell is just the dense value, so 100 here. So what happens here is that at every step, we're actually going to be multiplying a vector basically by a matrix of the input dimension times the output dimension. So in this case, from here to here, we go from 784 to 100, right? Does that make sense? So what we multiply is actually a 784 by 100 matrix between these two layers. So right here it's an n by 784, we want to go to an n by 100. So we multiply by 784 by 100 matrix, and it now becomes an n by 100. From here to here, we apply a 100 by 100 matrix. So we go from 100 feature, like a feature space of 100, to a feature space of 100. And we stop, so in terms of your question about why we stop at layer 3, we don't need to stop at layer 3. We can actually add another layer. We can add as many as we want, but this is an easy data set that we only need 2 or 3 layers to solve it. So if it's a sufficiently complex example or problem, we would add more layers. We'd add different types of layers to properly map the input to the output.
Just to follow up.
Yeah.
Sufficiently, how would you know that you need to add more layers?
So that comes through. So the metrics will be accuracy. So how well we can basically classify these images. And in terms of how we would add them, that comes through practice. It oftentimes comes through trial and error, but it can also come through some intuition. If you know that like problem shouldn't be that complex, then if you're being forced to fit a really complex function to it, you know you're doing something wrong. Does that make sense? Yeah.
Question.
Yeah.
Can you explain why you chose 100?
So, like I said to him, the choice of the numbers here is not really that important. This is a really easy data set. I can change the numbers to 50. I can change them to 200. It would still solve it. The point is that you see like how the dimensions of the inputs changes over time. Does that kind of make sense?
Right. So what's the difference between layer 3 and layer 2? Because
So they're distinct layers. So basically, they'll have different the values in the matrix that they represent will be different. But what they do is there are different parts of the network. So from here to here, the network is doing something. From here to here, the network is doing something. But what you'll need to notice is that the dimensions or the matrix size between layer 2 and 3 is different. Layer 2 encodes a dimension of 784 by 100, because you're going from a 784 input to 100 output, right? Layer 3, you're going from 100 input to 100 output, so it's 100 by 100. So they look exactly the same. Like it's visually deceiving, but they're different layers. They actually encode different numbers, and they're actually different dimensions too. Okay, any more questions? We can just ask away because it should be pretty, yeah.
What is a layer?
So a layer is basically something that does something to an input. So the first layer, it actually isn't a matrix. All it does is it takes the input and it crushes it. It goes from an n by, I guess we can just do it right here. So layer should be callable. Okay, so right here, you don't need to worry about that for the moment, but before X train goes through, the size is 60,000 by 28 by 28, right? Each of the images is encoded as a 28 by 28 pixel value. After it goes through it, After the first layer, what do we get? We get a 60,000 by 784. So it's successfully crushed the input. It's made it smaller, right? So we'll have to reload it here, but we can do it one more time here. So let's apply the same thing. Layer 2 of X train, and we'll print the X train shape. So since X train is already changed, we'll have to put it in. So, okay. This with that. Okay, I guess that won't work at the moment, but basically what, I'll just visually explain it to you. I guess it doesn't allow me to call it in that way. But what happens between these two layers is I just showed you that the input is 60,000 by 28 by 28. Then after layer 1, it becomes 60,000 by 784. It crushes the input. And then once it goes through one more layer, it becomes 60,000 by 100. So you're changing the feature space from 784 to 100. Then you do one more time, it becomes 100. And at the final layer, since we have a size of 10, we're just going to have 10 final things at the end. Does that kind of make sense? Yeah. Okay, go ahead.
So to clarify, we start out with a bunch of 28 by 28 like image matrices, right?
Correct.
Right. And then when you crush it, you just took up all those rows or all the columns and made it one like column vector? Or what exactly was the crushing? What is the important part?
Crushing, so crushing basically it just takes the input feature space and then it, the way it does it is it efficiently just takes the input and then puts it together. It just takes the first row, the first element, and it keeps it at the top and then moves the second row to its right, moves the third row to its right, so on.
Yeah, so you turn it into like one
Yeah.
long row.
Yeah, exactly. So let's move over to this one, just 'cause I guess the runtime was weird, so this one should work. Okay, so I'll just show the code at this point. Basically what we're doing next is we're going to be calling the model code. So we first call the tf.keras.models.sequential. What this does is it creates a model for us. So we have this model and we need to start putting layers into it. So the model class, it instantiates this model and then we add layers to it and then we feed input into it. So this model takes input, produces output, and it can evaluate accuracy and things like that. So what we do is we first add the layer 1, so we flatten the input, then we do the change the feature vector space to 100, then we do the 100 again, and then we bring it down to 10. So at this point, the input has gone from a 60,000 to by 28 by 28 to a 60,000 by a 10. That 10 is a probability distribution that we use to predict our classes. Does that make sense so far? So basically the next step is the compiling step. You guys can just copy that code there. So what this does is it takes the model and it attaches a optimization to it, basically an optimizer, which is the atom optimizer. This is how the neural network propagates the results, the loss, and then optimizes itself. And then we also have a loss. So I'll go into a little bit more about losses here. Okay, so this should probably make it pretty easy for you guys to understand what's going on. But basically, in our last layer, we have 60,000 by 10. It's returning a probability distribution. And there's only one true value. So this loss function it's iterating through all of the examples, and it's taking the mean, because we're doing 1 divided by n, and we're calculating this loss. Yij is basically the label. Is this a 0? Is this a 1? Is it 0 or 0 to 9? And then log Pij is the probability assigned to that label. So in our case, if the label was, if the label is, the correct classification is a 9, then the label would be 1 at that value at 9, and then the probability, you just take the log of the probability. If you take the log of a very small number, close to 0, the magnitude is a large but negative number, so the loss is large. Does that make sense? But if the probability is close to 1, for example, let's say your correct classification is 9, and your model predicted 9. You take log of 1, what is that? It's 0. So your loss is 0 for that example. So through this way, the loss is basically backpropagated. If you're successfully able to classify, you have a low loss and it's backpropagated through your network. Okay, so next part is model.fit. So this is the part that actually trains your model. So the model.fit API, what it does is it takes your input. So basically your 60,000 by 28 by 28, it passes it through your model and then automatically batches it for you and trains your model. So you can see on the bottom, it automatically gives you your accuracy and your loss, and it does this all by itself. In case you can't see, what it says is it trains on 60,000 samples, so your 60,000 images. It does 3 epochs because we specified 3 epochs. Epochs means how many run-throughs through your data set. So how many times do we go through 60,000 elements, train the element, and do a step on that, and backpropagate the result. And then on the right, it tells you your loss. So this is the average of the cross-entropy loss I was talking about earlier, and then your accuracy across the validation set. Does this make sense so far? Okay. So let's do the next step. So next what we're going to do is we're going to save our model. So we saved our model to an H5 file. So when you do this for your models, you're going to eventually save them somewhere and then probably run them in inference. But we save them to an H5 file, and then the next step we actually load it up to evaluate it. So we load it up and then we evaluate on our test set. So right here, what we've done is we've loaded our model from the H5 file and then we evaluate it on the X test and Y test. All it does is it passes the X test through our trained model and it evaluates the results based on the true labels, which is the Y test. So you can see that we got 96%, that's the accuracy, and then the average loss is something like 0.12. You can see that it's actually a little bit less than our training. Yeah, go ahead.
Did you say to train your model, you just use the API?
Say that again?
You said to train the model, you just use the API?
Yeah, so this is one way to train it. So I guess I went through it quickly, but model.fit actually takes the input, it batches it for you. It basically takes your input, optimally batches it for you, trains it for you, and then gives you the final model. So it just takes your existing model and fits it to the data. How do you optimize your model for that data?
So you,
Okay, if you have confusion, you can just answer. Yeah, go ahead.
After you're done saving the model in an H5 file, right?
Yeah.
How do you deploy it to your to a server, on a backend server, so that you can predict and send your results to a front end?
So you can store it onto like a Python-based backend server like Flask, as long as it has TensorFlow Keras installed. You can load it up there and then have it receive incoming requests. There's also
So like every time you have a request, you would call the H5 file and remake the model and then give the results back.
you can have it cached probably. There are various ways to have it deployed. You can look into the TensorFlow documentation for that, but yeah, that's one way to do it. Otherwise, yeah. No questions? Okay, so we've done that. So here is the last part of the code is basically we print out a pixelated input. So this is one of the classes. You can see that it very clearly predicts a 6, and then we predict a 6. So the loaded model.predict function, all it takes is the input, and then it produces a softmax prediction. So this softmax prediction, we'll just print that, is So this softmax prediction is actually a vector of size 10. The reason being is that the end of our model was a size of 10. So we're predicting a model like that, and then the reason we get 6 is that the highest value is right here, 9.9 times 10 to the negative 1. So 99% of the probability distribution is at the 6 value. So we take the NP to argmax and we get 6. And that's why it predicts 6. Yeah. Any questions about this? Should have been pretty simple. Yeah.
So it looks like your disk space is utilized like 40 to 50%.
Yeah.
So how much disk space do you have?
So this one, it's not much disk space at all. So we're going to talk about in the next step that we're going to use Google Cloud, where you can configure the amount of disk space you have. But for this one, the reason is I have a bunch of projects on Google Cloud, so it's not just this one. Yeah, I don't know about the specific details of how much disk space there is, but it's not that much. So if you want to train bigger models or your data set is bigger, where you need more disk space, Google Cloud or some sort of cloud platform is better because you can easily get more disk or mount a new disk for a pretty cheap price. Okay, so any questions about this work through? Okay. So the next thing we're going to be doing is the functional API. So you might have noticed that through that exercise that we just did, we added layers on top of each other. So we had an input, we added one layer, and then through that layer, the model data was fed through that layer, then it goes through another layer. It's very sequential, that's why it's called sequential. So the data has to follow one of many ways. But in some cases, you might want to have your model be able to branch. In that sense, like for example, your data has to go through 2 different layers and then they combine again, or they're shared networks. So for example, one layer is shared between 2 branching networks. Residual connections, you don't need to know too much about that, but basically you can have the input and add it after an activation. So in all of these examples are situations where the input doesn't flow sequentially, the data doesn't flow sequentially from input to output. You want to do something special with it. In that sense, you cannot use basically the sequential API. You need something a bit more complicated or more complex, allows you more flexibility, and that's what the functional API does. It's pretty easy to use, so it's not too complicated and it's pretty fast. So if you're planning to do something for the hackathon using deep learning or machine learning, this is probably the way to go. It gives you sufficiently flexible ability to do stuff, but it's also pretty easy to use. So the data set we're going to use is the Cypher 10 data set. So this one, what's going to happen? This is very similar to MNIST, except it is RGB data now. So it's 32 by 32 by 3 RGB data sets. And instead of just, it'll be 10 classes again. So instead of handwritten digits from 0 to 9, they're one of these things, like frog, truck, deer, automobile, things like that. So that's this data set. It's kind of different, but mainly the main difference is it's RGB. So what we're going to do in this exercise is use convolutional neural networks. Basically, it's kind of similar to what we did. It's actually very different from what we did before, but it follows a similar step in that we build a model using a sequence of layers, and we eventually backpropagate a loss. The only difference is the actual networks we use specifically. So do you guys, does anyone have experience or heard of convolutional neural networks? Okay, what are they about?
So for example, over there we had just number. Here we have 2, 3 objects, and instead of identifying the whole object on the picture, we can identify a part of it, a piece, some feature that we need to target.
Exactly.
We have a cat and a car, but we only be identifying cats rather than the whole picture.
You want to add anything? Okay, so yeah, he's very correct. The idea behind convolutional neural networks is that in images, the pixels around a particular pixel are important to itself. So if I was looking at a pixel at the top right edge of an image, it would be very important to look at the pixels right below and to the left of it, rather than correlate it with pixels at the bottom left or another part of the image entirely. So for this reason, because the pixels are heavily correlated with other pixels nearby, how convolutional neural networks work is that they look at these little boxes, they're called kernels, and they convolve. They basically move in boxes across the input image, and then they produce an output. So in this case, like this top left bar would encode something, and then it would go into an output. And we would slide the window down, look at the next box or square box, and then get some information about that and put it into the next layer. So usually the way they work is that they have these convolutional neural networks convolving information through a bunch of layers until we get nearer to the end, at which point we do dense layers again. So near the end, all the way to here, once we have a sufficiently complex model, depending on the data set, and we've extracted enough features, we then do some sort of a compression, kind of like the flattening. We get it to a vector, so we can apply dense layers on top of it. And at the very end, we do dense layers to get the 10 classes, just like what we did in the first step that I missed. Okay, so let's get started on that. Okay, so the first step is we're going to just import the TensorFlow 2.0 stuff. Give it a moment. Okay, in the meantime, you guys can start copying down these imports. So what we're doing here is we are importing the various models just like we did before. We're going to import something called batch normalization, which I'll explain a little bit later. That's a more complicated topic. Con2D, this is our actual convolutional network. So how we're going from the input, applying a convolutional layer. It's basically that con layer. The activation, so since we're using the functional API, we use an activation object to do that nonlinear mapping. So what we did the last example, we did, sorry, I'll just come back to that in a minute. But yeah, and then we have flatten just like before to reduce the size of the image. Input dense, you guys can import this, I'll explain everything in the rest of the code. So what we're doing in our very first, basically the first block of code is we're basically creating a con module. So in this module, we take in an input x. You can think of the input as x. Kernel size is basically the size of this convolving block. So how wide, how tall, and how wide is that block that we're moving across the input image. The strides is basically how much we're moving it across each image. So we take that block, we're sliding it are we sliding it just one at a time, or are we sliding it 2 units at a time, or more? And then the filters. So the filters is the last thing. This actually encodes the features. So we go from our input image, which is a 32 by 32 by 3. It's an RGB image, so it has color. That's why the last dimension is 3, encoding RGB. But the filters allows you to change that last dimension. So you can go from 32 by 32 by 3 to 32 by 32 by 10. So that last layer encodes the features of what the image contains. But the actual input size can be the same or not. So what we do first is we apply convolutional layer. So I'll explain a little bit more about what's happening here in this slide. It talks specifically about padding. So basically in Keras, there's 2 types of padding. I'll explain what padding is, but it refers to more about how the size of the image through the layer can shrink or change, or how you can adjust it. So in particular, you can see in the previous image that, as is common in most con networks, the image starts out wide but thin. So we have a lot of pixels in our height and width, but then the channel is only 3, so because we only have RGB. Later on, what happens is that this image, it gets smaller and smaller. The height and the width gets smaller through a con network, but then the channel gets bigger, so you can see it's gone pretty thick. And it continues to do that near the end. The image gets really small, but then the height gets pretty high. Channel size. And that's how you encode a lot of features into the image, and you change that into a dense, and then you can get good predictions. But what's happening here is we first take in an input as an image. It goes through a convolutional layer, but naturally what happens is, as you can see in this slide, the output dimensions. So how you read this is, the O means output, W in this case means the input dimension, so the height or the width. So output technically can be height or width. The W is the input, so the height and width of the stuff coming into that network. The K is the kernel size, so the size of that block. The 2P, P is the padding, which I'll talk about now, and stride is how much you're moving that block across the input and convolving it. So what we can see here is what padding does, padding equals same does, is that if you apply a convolutional layer through an input, if you have zero padding, or in this case same, in Keras terminology, it will keep the size of the dimensions the same as long as the stride is 1. So stride is, again, that level that you move your image, that you move the kernel or the input block across, and padding is that value. So as long as padding is equal to 1 and we have the same padding, we'll know that the input dimensions of the image, basically the height and the width, will be constant. And you can go through the rest of these, but I'll give you the example here. So in our example, our input images are 32 by 32 by 3. They're RGB images in that way. We have so our W is 32, our input and output is the same. We have a kernel size of 5, so that block is of size 5 by 5. And our padding is equal to the same. And then the stride is equal to 2. So our padding follows this formula, k minus 1 divided by 2. You guys can look that up online too. And the output, because of this transformation, becomes 16. But the important thing to notice, I guess, for this tutorial is that if you have same padding, if the stride is 2, your input dimensions get reduced by 2, both on the input and the output. But if they're not, then it will be the same regardless. So what's going to happen here? Does anyone have any questions so far about that long discussion on common networks? Okay. So we're going to create this model. So this applies a convolutional layer plus a batch normalization plus that ReLU activation that I talked about last time. Okay, the same thing here. We do a dense module. So what we do here is we assume that the input is no longer an image, no longer like 32 by 32 by 3, but is instead just a vector. And we apply a dense layer where the output goes from input units to output units. So I can put that comment like, so we go from n by input units to n by output units. And then we apply the softmax activation here. So the reason is that the output units has to be 10 in this case because we're basically classifying an image into 1 of 10 categories. So to explain that a little bit more, the con modules happen at every step of this image. Con module, all the way up to here, and then we have one dense vector here, one dense module here to predict the output. Okay. Any questions about the model architecture or anything like that? This next part will kind of clarify with you. So the way that this model works is we first take in the functional API. You have to give it something called an input, so it knows what the size of the data is going to be. And the data is going to be of size height, width, and depth. Later on, we're going to define that down here as 32 by 32 by 3. So it's expecting that input size. And you can batch it, you'll add another dimension, but each image is 32 by 32 by 3. So we first apply a single con module to the inputs. We add kernel size 5, padding, stride of 2, and filter size of 32. For each of these con modules, we're having padding is equal to same. So what's happening here is the input goes from 32 by 32 by 3 to 16. So we see that the stride is equal to 2, and where padding is equal to the same. So since the stride is equal to 2, we're dividing the input dimensions on both the height and the width by 2. So it goes to 16 by 16 by 32. So our filter size is 32, so it goes from encoding from 3 to 32. The next layer, what we do is we notice that our stride is 1. So that means our input dimension doesn't change at all. The height and the width of that image. So the input now goes from exactly as before, actually. So it goes from 16 by 16 by 3 by 32 to 16 by 16 by 32. Because our filter size is again 32, so that last channel would have size 32. Again, we divide our stride is 2, so can someone tell me what the image representation would be after this layer? So we go from, for the first one, our stride is equal to 2. We went from a 32 by 32 by 3 to a 16 by 16 by 32. The next one has a stride of 1, so it doesn't change. So it's again 16 by 16 by 32. So what happens after this layer? Our stride is equal to 2, but our filter size is 64. Yeah, go ahead.
Is it 8 by 8 by 64?
Correct, 8 by 8 by 64. Goes to 8 by 8 by 64. So similarly, you will do the same thing. At this layer, the input dimension divides by 2 again, but our filter size is 128. So so it increases there, and then we apply no filter. We put our stride size is 1 again for the rest of the model. So at the very end of the model, we have a 4 by 4 by 256 type model. Okay, if that's clear, then we'll move on to the next slide, which is going to talk about this global average 2D. So in our previous slide, in our previous example, we talked about that flattened layer. It takes an input of size n by n and then returns a vector, which is one dimension. Here instead, we have something like this. We have a batch size, so maybe 120 images that we're trying to train on. Each of them has 32 rows, 32 columns, and 3 channels. But now we want to flatten it we want to basically compress it or put it together, so at the very last layer, we can use dense layers and predict our output. So instead of using the standard flatten, we need to use something a little bit more special. It's called global average pooling. It basically takes the inputs across the channels. So if you think of this as a 3D image, you have maybe in the very last layer, in our case, we have 256 channels. So what happens is we take all of the elements and we just average them in each of these channels, and we output a size of 256. So at the very end, we have batch size times 256, whatever the channel size was at the very end. And using this, we put this through dense layers and then we get the output. So that's what happens in the next 2 steps. So next, we apply, the input is again x. After it goes through one layer of the global average pooling, we put it through a dense module. That does the softmax thing, returns a probability distribution, and then we have stuff in the output. So the way we compile this model or use it is we say model, and then we use the model class name. The inputs is basically whatever we inputted. So this input object, which is right here, and then the outputs is equal to x, what comes out here. So the powerful aspect of this is if you have more than one input, let's say I have input y as well. Let's say we're taking in 2 images and we're trying to identify how similar these 2 images are, or whether or not they are from the same reel, or maybe like the same set of frames in a film. And we have 2 inputs, so 2 32 by 32 by 3 images. We can have 2 inputs and then 1 output. And it allows us to construct things like that. So that's the main power of this functional API. Okay. Any questions so far about model architecture? Something like that? Okay. So the next step is we're going to do our learning. So very similar to the last step, we have an initial learning rate. Basically, this would be how much our model is learning, our batch size of 128. So this means that we're training on 128 images, 128 32 by 32 by 3 images, and then 10 epochs. So we train for 10. We train the training set for 10 times. The label names is basically the what we're trying to predict. So we're trying to predict one of these things. We load the data just like we did in the previous example. We divide by 255. Now each of the images is RGB. Each of these values is from 0 to 255. And then we print the test shape. So you can see we loaded the train X shape. Let's go back. It takes a little bit longer because this is a bigger data set, but the final shape is very similar. So instead of 60,000 by 28 by 28, we're actually getting a 50,000 by 32 by 32 by 3. Each image is 32 by 32 by 3. Okay, so in the last example, we passed in our data into our model just like it was. So we didn't do any augmentation or changing the data to make the model learn better. In this example, we use something called the image data generator. You guys can go look at that on the Keras website. What that does is it takes in the data and it applies transformations to the data. In particular, it's a data generator. So it provides data to the model based on the batch size of that model. So if the model batch size is 128, it would provide that data to the model at that rate. And then, so the model doesn't have to wait for new data to arrive. We'll be talking a little bit more about data generators in the next session after 1 hour. I guess it's already 11, so we'll have to move a bit quicker. But at the next part. But this basically provides that data quickly and it augments the data. So it shifts the data, it applies transformations. It does this so the model can generalize better. If you just give it the standard 32 by 32 by 3 data, it's not going to learn very fast. So we change the data and give it to the model and hopefully it can generalize better. So here we set up the model. So we have the input is 32 by 32 by 3. The output is 10. The length of label names is basically 10. So we're taking in these 32 by 32 by 3 images. We're producing a matrix where the number of columns is 10. Very similar to before. We're just using, instead of the atom optimizer, we're going to use the stochastic gradient descent, SGD. We apply some hyperparameters. So these hyperparameters you can search up online or you have to kind of tune them yourself. Or you can do stuff like grid search on them to find the best. But for now, we're going to use these because these are tested ones. We do the same thing, very similar to last time. We compile the model using sparse pedagogical entropy, and then we use the metric as accuracy. Okay, so this time, the only difference between this time and last time in our model.fit is instead of just applying model.fit on the input to the output, we actually do model.fit generator. This looks for a generator object in the input, and it looks for basically a generator in the input and then corresponding output. So here we have aug.flow. What this does, aug.flow, is it looks for that data. In this case, it's on our RAM. And it basically augments that data and then provides it to the model as a generator. So the model consumes data and then asks for more data. The generator provides that data. The model consumes it, optimizes itself, and then goes back to the generator to ask for more data. The generator, in this sense, all it's doing is it's being a little bit more efficient with the way it's providing the data to the model. Instead of just giving the data once and then waiting for the model to consume, it gives the data. The model consumes it, but while the model is consuming it, the generator is doing its next batch. It's pulling up new data for the model to run on. So it's for optimization as well. We train it. You'll notice that after 10 epochs, it gets pretty good accuracy, not the best, but after some time, it should get around 65 to 70% on this data set. So you can experiment with this model, you can add new conv layers, you can add new techniques to make it work better, but this is a decent working model for this. Okay, since we're running a little bit low on time, we're going to move on to the next one. But do we have any questions on this one? I know it's a lot of information. We're trying to cover a lot, but I'm just trying to give you the whole point of this workshop is to give you some code samples that you can use in your projects. So this code is given, the GitHub will be given to you. So if you don't catch everything I say, everything's on there. You can use that code on your models if you're going to look at it tonight. Okay, no questions it seems. Okay. Oh, sorry.
Just coming actually, just a quick question. Is there any way you can fix the contract? It's actually kind of hard to see.
Oh. I don't think I can do it on my machine, to be honest. Let me, I'll continue for now, but I'll put in the request right now. I'll just tell you from the
It seems fine when you use dark mode, so you can switch to dark mode somehow.
They had this issue earlier, and
Yes.
the tech people came in and fixed it.
Okay. Let me just message it right now. Okay, we'll move on for now. I'll just read through it. It's not too bad here. So, I can't really find that. So I'll just speak through it. So basically, what we're going to do the next step is the last thing that we're going to cover for this workshop. We did sequential, we did functional. Now we're going to do subclassing. So this is the most powerful technique in the sense that gives you the most flexibility to write your models. So you can do it you can change the way you implement the forward pass of your model. You can implement things like early stopping for training. You don't have to wait for the model to finish an epoch. You can save the data prematurely. It's generally preferred only if you're trying to re-implement a paper or try something very new. So I wouldn't really try for the hackathon. But there's some cases where it might be useful, or like if you just cannot use the APIs, like functional API doesn't have what you need, then you'd have to resort to model subclassing. So, like I said, you can write your own custom layers, you can develop certain networks with branching that's hard to do with functional API, which we'll cover in the next one, and then your own training block loops. So, I guess you guys cannot see this, but this exercise, what we're going to cover is autoencoders. So, have any of you guys do you guys know what autoencoders are? Anyone know? Okay, it's basically a data compression algorithm, specifically feature compression. What we're trying to do is we're trying to go from an input object of a certain feature space, maybe an image, like we did in MNIST. In this particular example, we'll go with MNIST. It has 784, so we're trying to predict an output. Basically, the image is composed of 784 pixels, that's the feature space. But in some cases, that's too expensive. It's not compressed enough. So what we're trying to do is we're trying to create a model that compresses that data. The way it works is the model iteratively computes a smaller feature space. So our input maybe of this size, so it has 10. The feature space is 10. Then we go through a hidden layer, it becomes 6, and then our final part is 3. This code thing is what you call the compressed version. And then we go through another 2 layers and we produce the output. What we want is that the input and the output to be as similar as possible. So we go through one compression, we decompress, and then we check the inputs and the outputs. If they're really closely similar, then we know that we have a good compression algorithm. Does that make sense? The problem statement's pretty easy, right? Okay, not quite yet. So, okay. So we'll do the same thing. So we're going to run with TensorFlow 2. Okay, then we're going to import TensorFlow, PyPlot, and everything. So the next part is where the subclassing happens. So you can see that the structure of our code has changed. We're no longer defining model and then adding layers. We're no longer having like a function that creates a model. In fact, we have a class now. So what this model subclassing is doing is you have a Keras model and you have Keras layers. What we're doing is we're subclassing that, we're making our own subclass out of that, and we're modifying the attributes. So we're inheriting things from that superclass, which is the Keras model or the Keras layer, and then we're applying our own forward and init functions. So basically for Keras layers, if you're going to use model subclassing, you first change your init function and then your call function. So I'll explain what they both do. So init, what it does is you first mention that this is a subclass of the superclass, which is Keras layers. So in this step, we're actually taking a layer, which is one layer, and we're trying to implement that. So if you remember in our previous examples, we had things like this. Layers.dense, like mainly layers.dense, but on the other one we had layers.con, things like that, right? Here what we're doing is we're trying to implement our own layer. So what we first do is we set in our init our latent size dimension. What this means is this is what we want our image to go to, how compressed we want it to be. Our intermediate dimension is basically this. So this is latent, so if you can see my cursor, the latent dimension is how small we want to get. The intermediate dimension is that intermediate value. We go from the big to the intermediate to the small. And then our input is a 784 image size. Does that make sense so far? Everything makes sense? Okay. So what we first do is we have flatten. So we want to flatten it to make it easier. Then we apply a Keras dense layer to this. So this might seem a bit weird. You're like, why are we doing that inside of our own layer? So a Keras layer, when we subclass it, it can actually be consisting of many separate layers. Many of the basic, you can so-called primitive layers. So inside our encoder layer, which is going from the input to that output, the input to the code, we have first we go from the input dimension, which is 784, and we compress to that 128. So we go from 728 to 784 to 128. We apply the same value activation. Then we do one more compression. Instead of going from, so this time we're going from the 128 to the 32. So I'll just make that clear. Press from 184 to 128. So this is our input, intermediate, and output. So next we make a call function. So the two things, init and call. Call is basically what we do when we, very self-explanatory, when we call the function. So first what we do is we do the flattened input. So we call the self.flatten layer, which is the Keras layer, which is the Keras flatten layer. So it's very basically what we're used to. Then we compress to our intermediate space. So from here, this would go from n by, let's just say, n 2828 to n 784. Here we're going from n 784 to n of 128. The intermediate space is 128. Then we do the same thing, we go from n128 to n32. N32. And then finally we return that latent space. So the latent space is our final true objective. We want that to be as good as possible, right? So that's what we're trying to get to. Now the decoders class is the other step of this problem. It is this half of basically the diagram. So in this step, what we do is we have our input. Our input is no longer going to be 784, it's actually going to be that latent space. So it's going to be n by 32. So we're going to call n by 32 our latent space, and then we're going to decompress to our intermediate. So our dense layer has units of intermediate dimension, which is 128. So we go from n32 to n128. Then we do the same thing here, except now we go the full way. So now We go N128 to N784. So now we have 2 steps of our decompression process done. Any questions about this? Do you guys get it? Okay. So we do the same thing, we call it, so we first do the decompressing to intermediate and the decompressing to actual. So now we constructed our 2 layers. Our first layer encodes or compresses, our second layer decodes or decompresses. So in our model, we do the very similar thing to what we do to our layer. We first specify that it is of type, it is a Keras model. We're subclassing from that, so we need to inherit those associated methods. And we instantiate our encoder and our decoder. So our input is now the n by 708, n by 28 by 28. So n by 28 by 28. So if you remember our encoder, it takes that n by 28 by 28 and then it produces an n by latent space. So now after this it becomes n by 32. Now we take this compression and then we decompress it. So we get the reconstruction. The reconstruction is basically the decompressed latent space. So now it becomes n by 784. And what we want is that we want this decompression, reconstruction to be as similar to our flattened input as possible. We're trying to get them really close to each other. We want the pixel values to match as much as possible. So that's our training objective. Make sense so far? Okay. So our reconstruction loss, what we're going to do here is, this is basically a function that takes the reconstruction and the actual. So the actual is our input, the flattened input. So I guess I'll put that here. Actual equals flattened input. And we basically do a tf.math.square difference and we reduce the mean. What this means is that our input is going to be n by 784, our output is going to be n by 784. We take the difference, we square all the values, and we take the mean. We want that value to be as small as possible, right? We want the deviation between the inputs and the outputs, or the actual and the reconstruction to be as small as possible. And that is our loss. Reduce mean, all it says is that you take an input and you just calculate the mean across it and give it to the loss. Okay, I'm not stepping through this, so I'll do that right now. Okay, we load our data very similar to what we did in the past. Okay, so now what we're going to do is we're going to use a different type of technique. We're going to use the tf.gradient. So instead of using model.fit, we're actually going to pass in batches ourselves and train on that. So this is not necessarily a part of how subclassing works, but this is another way to write ML code. Instead of using the model.fit, we're gonna create our own training loop, and we're gonna feed in data through batches and train our model, and then give the results. So what we do first is we actually create batches. So we have a function. All it does is you feed in a batch size. It makes sure that the batch size is that 60,000 is divisible by this batch size, because there's 60,000 training examples. We want to evenly give each training example into a batch. We calculate the number of batches. Then all we do is we go ahead and we take the input, which is an array in this case, and we make it into an array of lists. So each list is a number of examples in that batch. Okay, so does this make sense? So in this case, what we end up getting is a list of lists, or we can say array of arrays, and in each array in that big array is a batch, and each of those elements is a training example. Okay, so now we're going to do our training step. So what we're going to do is we're going to call we're going to set up our batch size, it's 200, our number of batches, which is 60,000 divided by 200. So we're going to go through this 300 times, and then our number of epochs is 10. So the way we start this is we initialize our autoencoder, which is the autoencoder instance, or inst. and we initialize that to our object that we defined above. We specify our optimizer. We're using Atom again this time with this initial learning rate, and then we create batches. The batches are these things. Okay, so this is the training loop. So instead of a model.fit, we use a training loop. So what we do here is for every epoch, we go through every element in every batch in that batch array we made, and we train on it. So what we do, so every epoch we iterate. For every batch we do something. This tf.gradient.tape as tape, what it does is it basically takes the model that you created, the Keras model, it finds all the trainable variables. The trainable variables are basically the arrays that the matrices I talked about that go from one input to the output, and it zips them all together, and it basically watches them like a tape, so it puts them together so that Keras or TensorFlow can find those trainable variables and apply gradients on them. So you didn't need to do this for model.fit, because in model.fit we pass in the model, it automatically knows where all these trainable variables are. But since you don't have since you're not using the default training and you're creating your own training loop, you need to tell Keras what gradients should I look at. Otherwise it wouldn't know. So as tape, so not needed for model.fit. Okay. So what we do is our reconstruction of the batch and our flattened input, we first do a forward pass. So we take the batch is of size 200 by 28 by 28 by, 200 by 28 by 28, and then we pass it through. Our reconstruction will be 200 by 784, and then we do the loss, the reconstruction loss between the reconstruction and then the flattened batch, which is the input. So this flattened batch is essentially the input, except it's just been flattened on that last layer. So instead of being 28 by 28, 784. We calculate that, and then we do the gradients. So this is the other thing. Tape.gradients, what it does is it takes the loss function, and then it takes the model's trainable variables, like what I just mentioned, and then it creates that gradient for you. This is the step that actually creates the gradients in the network. And then finally, we apply the gradients to the network using this optimizer.apply gradients. It basically takes the hyperparameters in your optimizer pump, your initialized optimizer, and applies it to the trainable variables. So the trainable variables are your model, essentially, what defines your model, and then your gradients are how we should change that. And then we do our epoch loss, and then we, at the very end, we can just look at how it goes. So it should be pretty fast. So you can see now that I have to manually print the epoch loss, so it goes epoch 1, it trains. So one other thing you guys can do when you do collabs, you can actually change the hardware accelerator. You can go to runtime, change runtime type, and you can choose GPU or TPU. Probably GPU is only needed. You guys are not going to do anything too complicated, but this will rapidly speed up your training time. But for now, we can just let it go. But yeah, right now what it's doing is it's training on each batch. You can see that the loss is decreasing as it should be. So over time it should get better and better at what it's doing. And after the 10th, it will output the example. Okay, so you can see that this is our input, the 2. It goes to the data compression and it gives. So it's not a perfect data compression scheme, but it's learned something, right? So we've done like even a very basic autoencoder produces something decent. Okay, so that's pretty much it for this part. The second part is going to be much longer, so we're actually not going to do that. I'm going to put up the code that you guys can take a look at. But it's basically very similar to part 2, which was using Convolutional Networks. Because right now, you can just open up the floor for any questions. If you guys have any questions about what you want to work on, I can give maybe some advice on how you can implement that for the hackathon. Okay, I guess that's it then. So one more thing actually, so do you guys have Google Cloud credits? Or you guys have that? Do you have that with you? You guys have that? Okay, so we'll actually do a quick workshop on that, maybe just how to use the Google Cloud. So So if you guys can plug your laptop, we'll just do that right now. If you don't have it, that's fine, we can just do it here. So the fastest way to get Keras stuff up and running is if I go to my Google Cloud right now, we have our VM instance. So you just click create instance here. There are a couple of things that you want to do, because if you want to install TensorFlow GPU, you need like CUDA installed, but there's some tricks that you can do. So first maybe everyone can get on Google Cloud and go to that page, VM instances, and then go to here to click to create instance. So I'm just going to teach you guys how to create a GPU instance on the cloud to start training stuff. So click create instance. Let me know if you're following along once you've gotten to this step. So you don't want to do it?
Can't see.
Oh, right. Okay.
There.
Okay, I don't know. Let's see if we can do. Let's install this. Okay, can you see better now? Okay. Loading. Okay. Why is that? I think that's causing some problem. Yeah, I think it cannot be doing this. Okay, let's find out. So once you get onto console.google.com, there should be a bar that says create instance. You should go there. So I'll just get onto this read. So have you guys put up your Google Cloud credits onto your account yet? Okay, and you've done that too? Okay, maybe we can do that real quickly so we can access this. And you put it up? No? Okay. Do you have the credits on you?
Downstairs.
Okay. No worries, you can just hold on. I'll just go over with you then. You don't need to actually do anything. I'll just create it for you. So you can create an instance name. The main thing that you want to do here is you want to give yourself a little bit of extra CPU RAM. And then in particular, you want this disk image to be changed to TensorFlow. So if you don't do this, doing TensorFlow GPU is installing TensorFlow GPU is going to be hard because you need to install CUDA and everything. So you scroll all the way down to the deep learning image TensorFlow 1.15. Give yourself a little bit of extra disk space if you're going to be doing anything intensive, so 300, so you don't run out of disk space and have to mount stuff. You click select, then you go here to CPU and GPU, you add a GPU. So the cheapest one for this is T4. The cheapest globally across the Google Cloud platform is the K80. That should be like about $1.5 an hour. Relatively cheap. You can get a lot of value with 300 credits that you have. And then your persistent disk is done, and then you can click create. So this will create an instance for you. So the main benefit for this instance is that you have TensorFlow GPU pre-installed. So I'll just tell you the last step that you'll need to do. Give it a moment for it to connect. Are you able to walk through or not really?
It says getting ready.
Okay, getting ready. Cool. we're able to, you can see like it started, so we SSH into it. So the main thing that the first thing that we do here is it's going to ask us for okay, so now we're connected. Usually it takes about a minute or two after the instant start for the first time that you'll be able to get here. So you'll see that with this instance, it actually has CUDA and TensorFlow GPU pre-installed, so you don't actually have to go to the trouble of getting CUDA installed, which is a real benefit. You just click Enter yes, and it'll have the NVIDIA driver installed for you, so you can automatically use your GPU code, your TensorFlow GPU, and your PyTorch GPU if you want to use PyTorch automatically. And yeah, this is pretty much it. So this is pretty much the end of the tutorial. If you have any questions about Google Cloud or how to train stuff on the cloud or any of the examples I went through, you can ask me now. Or I'll be here probably for the next 15-20 minutes. So if you have any questions, just feel free to do so. Thank you.